Hey guys, welcome to Math 140. I'm going to try this for the third time. So we're going to start in Chapter 1, Section 1. We're talking about Euler circuits. Now, before we can get to Euler circuits, we've got to talk a little bit about a model. Now, a model, especially a math model, is a reduced form of the problem. And when we say reduced, it's usually done in a couple of ways. First, we throw away information. Now, you don't know when you're first doing it if you're throwing away good information or not, but we throw away information. Second, we usually try to create a picture, possibly some equations. I'm sure you remember that from high school. But there's something else that we want to do, is we want to identify certain characteristics in the problem that are useful. Now, a good model is a major reduction of the problem. So, for example, I'm going to draw a very simple model. You guys look at it, and I think most of you know what I've just drawn. It's a house. But I've drawn it a little bit tall, and you know how on ACT exams or SATs, they say the picture may not be in proportion. Is that a two-story house? Is it a big house? Is it a small house? Where are the windows and doors? All of that information has been thrown away. However, we've retained characteristic. It has apparently a slanted roof. It appears to be rectangular. And we made a picture. We don't have any equations. Now, typical in geometry and other things, you would start labeling width and height and length, but we're going to stay heavily away from that type of thing. We want to know pretty much all the time what the least number of variables we can do in the problem and identify the ones that are really important. Now, let's do a map. Why a map? Well, because a map is a major reduction of information. So I'm going to draw a couple of blocks. Oops, I didn't mean for that one. I want this road to, that's not there. And I want this road to go up here and away, so it's like 3 blocks in a town. And now I'm going to put some houses on here by just putting some dots. Now, if I don't tell you which way the houses are facing or the driveways, these roads could have a particular use, and, well, it could present a difficulty in our problem. So let's just do the following. Let's also say how they connect to a road. We're going to put another one here, and another one here, here. So let's now do the following problem. Let's suppose a trash man wants to pick up the trash. And he can travel any road, and he'll walk to either side of the road to pick up the trash. Now what's interesting about this is that even though this is a model, it's already got too much information. I'm going to reduce it. I'm going to reduce it to a lot less information. First off, this dot, this dot, this dot, this dot, this dot. I've reduced the intersection to 8 dots. And now the roads themselves, right here, right here, right here, here, right here, 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 here. So I've reduced the map now to the following roads. And in fact, I've thrown away the houses. But I'm going to tell you what the roads mean. The roads don't mean it's the road. It's a required path that the man, that is the garbage man, has to cover, because there's a house that faces this road. There's a house that faces this road. House that faces this road. House that faces this road. These two don't really matter. I've already got one on this road. House that faces this road. House that faces this road. House that faces this road. So what happens here is every single one of these green edges represent the need to go on a road. Doesn't talk about how many garbage cans he's going to pick up. He just has to drive that road. So now we have a picture which is called a graph. It's composed of vertices and edges. Now what's really interesting is I could have drawn a picture, but I could have used in equations and letters, and I'll show you that it makes it kind of more complicated actually. If I write this as A, B, C, D, E, F, G, and H, and I give the vertices names, well then the vertices can be listed as A, B, C, D, E, F, G, and H as a set. Now the edges, though, are much more complicated because I have to say that they're between two things. Now if I write down AB, that means there's an edge from A to B or an edge from B to A. We don't care which. And then there's BC, and then there's DE. Notice I'm doing the horizontal ones first. EF, GH. This is kind of a systematic approach. AB, BC, DE, EF, GH. Now I'm going to do the vertical ones. AD, BE, CF, EG, and FH. And so this picture is all of these letters put together in some form there. That's kind of weird. But I'm going to demonstrate that this would have been enough to draw it, actually. So I'm going to continue here. I'm going to make use of that list of letters, and I'm going to draw a graph from that letters without having the original picture to begin with. And I'm going to do it kind of sillily. So I'm going to go A, B, C, D, E, F, G, and H. I just put the dots around. So now I've got A, B, C, D, E, F, G, H. Now I'm going to write in A, B. And so I'm going to grab a different color here. So I'm going to put in A, B. Got it. Oops, I didn't mean to. A, B. Now I'm going to put in B, C. Now I'm putting D, E. And then I'm going to put in E, F. So far, so good. G, H. Good. A, D. There. After A, D, oh, I wrote terribly, but that's a B, E. B, E. C, F. Oh, it's kind of hard to get there. It looks like I'm going to have to, like, cross my lines there, edges, but it's not an intersection. It's a crossing, but let's not worry about it. E, G. I think I can get that one. No, I got to do that again. Oh, E, G, and F, H. Man, that nasty graph. Do you suppose this is the same information as that? Here's a challenge for you. You don't have to do it, but I want you to think of this being made as beads, A, B, C, D, E, F, G, H, as beads, and the edges as strings. Can you see that we can pull the GH out over here? I'm going to show you how we can remanipulate this. So let's put the G in a new spot and the H in a new spot, and this would be gone. But now the FH would have been here, the GH would have been here, and the EG would have been here, and you can see this square forming right there that wasn't in the picture before. and that part's gone. And you know, you can keep doing this, and what happens, you can lay and read this and make it that. This information is nicely organized here, not so nicely organized here, but both of the graphs are the same. Now, a man by the name of Leonhard Euler was given a problem to solve by a person who wrote to him. Mathematicians at one time used to be famous. People liked to talk to them and ask their opinion about things because, well, there were very few people that were really good at solving lots of stuff. They wanted to walk around a city, and they wanted to visit these beautiful bridges. It's a Czechoslovakian city, I think. The bridges were adorned and decorated, and basically, when you made this map, look something, maybe one more bridge here. All right. So what's going on here is Euler had put together the spaces. So each of these vertices were actually land. And each of the edge represented a bridge crossing water into land at another spot. So the model represents a town, but they shrunk all of the land to a point and they put the bridges there. And someone asked Leonhard Euler, I live at my house, and on Sundays I'd like to go for a walk and visit all the bridges and come back home, but cross each bridge exactly once. So first off, some vocab. We have vertices or vertexes. We have edges. And they represent something, but they don't necessarily represent relationships as we perceive them as all the time. That is not unusual. For example, if you take a look at the book, they have a picture of New York, London, Miami, Rome, and Berlin, and they move it around, and Rome is south of London. Well, that makes sense. New York is north of London. Does that make sense? Miami south of London, that makes sense. But what happens if you move it around like they did and you got them in different spots? Well, it doesn't matter. The graph represents relationships. This is a relationship. This piece of land and this piece of land has a bridge between it. Really doesn't matter if that land's north of that land or not. Now, when you traverse a graph, there are several ways to do that. The first and most common one is to simply have a starting point. Doesn't matter where, really. Sometimes it does. In this case, Euler was trying to find a circuit, which means you come back to where you started. So the word circuit means to come back, and then we have that strange word home. But, you know, if you have a circuit and your friend lives on your circuit, he can do your circuit and just get back home as well. So circuits are cool. A route is where you start someplace and end someplace else. So in this picture here, I'm going to put there's a route. That route starts here, ends here, and I can label it 1, 2, 3, 4. So it's reasonable that's the start, but that is not where he started. So this route here is an odd route. It's an unusual route, rather. It visits every piece of land, but it doesn't visit every bridge. The focus of this exercise is to visit the land. Well, Leonhard Euler discovered that in order to visit everything and come home, you have to go into something and come out. Next time, go into something, come out. Now, something might be visited more than once. Imagine the following. Imagine the following. You have a piece of land that has 4 bridges come into it. It's very possible that a route would come in and then leave, and much later come in and leave. But notice, in order to be going around and return back home, wherever it is, you go in and out of a vertex. So what Euler discovered is Euler's theorem. And this is a very interesting fact, and it's a very nice thing to start with right away, because it exposes how mathematicians think. The first thing that Euler wanted to do was determine, should he bother to even attempt the problem? What happens if something's impossible? I mean, can you make a Frankenstein? Can you undo an atomic bomb? I mean, these are things that realistically, we can't do. So I'm going to draw that land picture again that I had. And I'm going to put the bridges in again. And Leonard Euler's theorem says, for this particular problem, don't even attempt it. Because what he did is he looked at each vertex, a real small bit, and because of that idea of things coming in and out, he said, I'm just going to count the roads, or in this case, the edges, or in this case, the bridges, coming to a point, 1, 2, 3, and he's going to write these numbers down, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. And these things are called valences of a vertex. We also call them interchangeably the degree of a vertex. Euler said, you can't find, or there doesn't exist, a circuit visiting every edge exactly once and coming home if any vertex is odd. So his theorem says, if any valence is odd, there is not a circuit visiting every edge exactly once. So in this problem, Euler, the mathematician, said, don't even bother to try. You can spend your life on it. You can't find a starting point, visit every edge exactly once, and come back home. The oddness of the vertices are bad. However, Euler said, well, maybe you're willing to go out and end someplace. Like, let's say you're on a pilot that's got a route. He flies from a city. The flight is an edge. So a pilot's doing this, bouncing around. And then that's the end of his day. So he went out. And here's where he started and here's what he ended. But now the interesting thing is, in the next day, he can reverse it. He can do this and this and this. And he can get home. This, when you start and end someplace and visit every edge exactly once, is called an Euler route. If you visit each edge exactly once and come home, that's when you have an Euler circuit. Well, Euler said, I know even when routes exist. If two vertices have odd valence, you have a route. And that route starts at one of the odds and ends at the other odd. In this picture I just had here, that was an odd 1, that was an odd 1, that was a 2, 2, 4. And so you had to start and end at one of the odd ones. So Euler had a theorem. He said you can't do it if you have any odds. But if you have exactly two odds, you can find a route, start and end at different places, visit exactly once. Otherwise, everything's even and you can do it. Now, what makes Euler special? Well, first off, as a mathematician, he was one of the first to start drawing these graphs of massively reduced information. And he was the person to define valences. And he said, when you can solve this problem, The weird thing is he didn't tell you how. Well, the answer to the how is just guess, and if you mess it up, fix it. So let me do one here. I'm going to make a lot of All right, so this is my graph. I'm going to make my dots, my vertices much bigger. Apparently, I have trouble keeping track of the top. So there we go. So now I'm going to put in the valences. 1, 2, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Well, every vertex is even. So you can start someplace and end someplace. And you know what? He doesn't tell you how, because just try it. And if it doesn't work, fix it. So let me demonstrate. Let's suppose this is your start, your home, and you did the following. You made a mistake and you simply, I went out 1, 2 came to this one, 3 came here, 4 came home. And I just went zoom, zoom, zoom. And unfortunately, that little route, it's a circuit, but it doesn't visit every edge exactly once. You miss some. So I'm just going to write this down. You did 1, 2, 3, 4, 1, 2, 4, and it's, oops, it fails. So I'm going to fix it. Find an edge you didn't traverse. So here's one, this guy here. So what we're going to do is we're going to go 1, and after 1, we're going to go 1, and then we're going to go 1.1. We're going to go off from the place that we said, oh, we should have done this. 1, 1.1, and now I'll try this 1.2. Try this 1.3. Then I'll go here. 1.4 is my edge. Then I'm going to go down here. Edge 1.5. Now I'm here. I have to leave 1.6. And let's go back up here. 1.7. And now we reached here. We'll pick up with edge 2, edge 3, edge 4. And that was my attempt to fix it, and whoops, that didn't work in it together. This one was bad. Now, we missed this edge that leaves after 1.1, 2, 3, 4, 5, 6. That's 1 point. Can't read my own writing. 1, 2, 3, 4, 5, 6. That was 1.7. So right after 1.7, before 2, right after 1.6, before 1.7, I'm going to do the following. I'm going to use exactly the same edge labeling. But when I get 1.6 here, I'm going to cut it. I'm going to go here as 1.6.1, just like notes you take in class, subsection. And then back here, 1.6.2. And now I'm back to 1.7, and now comes 2, and then comes 3, and then comes 4. So you fixed it. This is called the cut and fix algorithm. Just find one that you missed and fix it. Now, this algorithm has no name attached to it. It's just guess and check, but if you fail, you can fix it. So, Euler circuits, Euler routes, Euler problems. So we want you to look at ones and find these Euler circuits. So you now about valence and the like, and we've reached section 1.3, and that will be good for our first lecture since we got to catch up and kind of hang tough there. So now, in the e-book, there are some problems. So there is the skills check. I don't assign those. We don't do the skills check. I assign the exercises. Now, the problem with some of these exercises is you have to draw pictures, and you have to just figure some things out. So first off, problem 2 is pretty straightforward. It's nice and easy. Problem 4, I think it's got a little bit more to it, but not much. It's mostly practicing your definitions. Then problem 10 has some more meat to it, and it asks you to go back to a previous picture. So it's kind of like 2 problems in one. Problem 14, and this has got several parts to it. It also has you go back, fortunately. Problem number 24, and then lastly, problem number 30. So those are the exercises, and those are at the end. They are out of section 1.1 and 1.2. All right. And I will include those in an email when I send them out. Now, since it's uploading very late tonight, that means that you'll get 4 days. So what's today? Sunday night. So then Monday, Tuesday, Wednesday. These will be due on Thursday. And I will send out an email telling you how to submit your problems.